calculating the mass of a black hole. The problem is to find the mass of a black hole given what we know about the gravitational forces and the forces due to curve and motion. I obtained this result by equating that net force to that force due to the gravitational pull of the black hole on the star, because there is no other force acting on the object. So after I equated that to, the mass was determined to be the magnitude of that net force times r squared over g times the mass of the star, which is 3.979 times 10 to the 31 kilograms. So in relation to the physical system, as stated earlier, I equated the two, where r is the distance between the star and the black hole. Star.m is the mass of the star, which is 1.989 times 10 to the 30 kilograms, and delta t is 86,400 seconds, or 1 day. So next I had to represent that in the computational model. So I determined that I needed to find the dp over dt, which I then equate to Fnet. So to first do that, I need to find the velocity, which is just the change in position over the change in time. And then I need to find the initial and final velocity to find the initial and final momentums. So to find the initial and final velocities, I just did the velocity at index minus 1 and the velocity at the index. So I just did delta v is v final minus v initial, and delta p is star times delta v, where dp dt is just delta p over delta t. And I set Fnet equal to dp over dt, and I'll explain why later. So I said the radius is equal to the position, where that position is just the relative distance from the x and y position of the location of the black hole and the x and y positions. So the square root of that squared. So as stated earlier, the mass of the black hole is equal to the magnitude of Fnet times the radius squared divided by the gravitational constant divided by the star's mass. So when I run the module, I get that the star's mass or the black hole's mass is indeed 3.979 times 10 to the 31 kilograms, which WebAssign determined to be the correct output. So next I look at what does it mean. My program uses F perpendicular, F parallel, and Fnet for the arrows. And I set these quantities equal to dp over dt perpendicular, dp over dt parallel, and dp over dt respectively. This is because force is a theoretical quantity dependent on the values yielded by experimentation. There's no way to directly calculate force. In this lab, the forces were dependent on the respective changes of momentum over time, which can be predicted because we know the position and delta t. So to find the perpendicular and parallel forces, I normalized the initial momentum, and then I took the magnitudes of the final and initial momentum and divided that by the change in time. And then thus dp over dt parallel is just that normalized momentum times the change in magnitudes. And Fnet parallel is just going to be dp over dt parallel. Fnet perpendicular is just dp over dt, which is what was initially calculated, minus dp over dt parallel. So for the what if question, it asks if we could tell the difference, given that the position and the mass of the star are the same. In short, no, because we use the notion that Fnet's magnitude is equivalent to the magnitude of the gravitational constant times the mass of the star times the mass of the hole over r squared. Now, because the relative positions do not change, r squared does not change. Next, Fnet is dependent on the change of momentum of the star over the change in time. The change of momentum of the star is just the mass times the change in velocity. And we calculate the change of velocity by calculating its initial and final velocity with the time step of 1 day. And most importantly, we calculate that velocity by dividing the positions by the time step. So because of that, our Fnet is dependent on that position and delta t. So because the star's mass does not change, Fnet does not change, and the position does not change, we would still use this equation and yield the same mass of the black hole. So it would not be possible to find a different value for the mass of the black hole.